Okay, last time we started the topic of spot speed studies. We are covering the outcome which is related to traffic data collection and analysis, and we looked at what do we call as spot speed study. Okay, so there are some conditions which you need to meet before you can use this data for spot speed analysis. We looked at what are the uses of spot speed data, but the main thing is we are trying to use the choice of the driver in our design. Okay, we are looking at what impact the choice of driver has on the road design and road accidents. Okay, some things we have discussed already, most of them. Okay, apart from 85th percentile speed, I will come back to standard deviation. I don't know how I missed it, but we have missed it. Okay, I'll come back to it. How do we collect spot speed data? Once we collect it, we have to have it in the form of frequency distribution, where the speed is in groups, and for each group you have number of observations. So we don't have raw values, we have groups and observations. And then using this data, we plot frequency distribution graphs. The first one is based on frequency of each group. The second one is on cumulative frequency. Using the data, we can calculate two types of statistics. One is central tendency, the other one is dispersion. The central tendency tells you about the middle of the data, where is the center of the data. Okay, and in that regard, we have discussed mean, median, mode, and pace. Okay, so all these tell you about the central tendency, where is the center of the data. Okay, and it could be a value and it could be a range. It could be a central value, it could be a central range. Okay, so for example, if you take mean, median, mode, and pace, okay, which one of them is a range? Pace is a range. Okay, but again that has to lie in the center of the data. Where now one more thing, when we say the center of the data, we don't always mean the middle value. Okay, there are other people in the class, not only boys. Give it to him as well. We're waiting for you. Everyone attend?
Yes. I make for them. I make attend for everyone.
Do it for yourself. Okay. When we say the central value, we want the normal average value. Okay, and that may not be the middle of the data. So if your data is from 30 to 60, like our data is from 30 to 60, okay, what is the middle?
45.
45. People are still thinking 30, 31, 32. Will I get the middle?
Never.
Anyway, so around 45. So I'm not looking for 45. Okay, I want to have a value where most of the people drive, which is selected by most of the people. Okay, so the mode is a good representation of that. When we calculate mean, now you see mean, the equation of mean, we are using number of values here, right? Number of observations. So if the number of observations are higher for a group, it will have more weight in the mean. Okay, if you look at the equation, number of values into the group, right? The number of values are higher, the weight of that group will be higher, right? Okay, so the idea behind central tendency is not to find the middle value of the data, middle value of the speed. We want to find the speed which is chosen by most of the drivers. Got it? That's why we have the frequency distribution. That's why the mean equation is changed, and that's why we calculate the mode and the pace and these things. Got it? Clear? Okay, so these things may not always lie in the dead center of the speed values. Okay, even in our case, it was not around 45. Okay, the mean was not 45. The median is, you can see here, is not 45. The mode is not 45. Okay, so you can be ahead of the middle value or below the middle value. Okay, but these are the values which are chosen mostly by the drivers. Got it? Clear? Okay. Now we move towards other measure of other type of statistics, which is statistics of dispersion. Okay, these statistics tell you about the variation in the data. In other words, how far from the center the data goes. Okay, how far from the center the data is going. Okay, in both directions, plus or minus. Okay, so the first, everybody did this. Okay, the first measure of dispersion we will discuss is standard deviation. Okay, now who knows what is standard deviation? Who knows what is standard deviation? People who are running YouTube channels on statistics.
I'm checking this road. I think it's wrong.
Yes, wrong, obviously.
That's summation.
Yes. Everybody done? What is a standard deviation? Yes.
Like an error.
It's like an error. And what it is really like? Error how? Tell me.
When it's high, that means values have a large variation.
Okay. Okay. Anybody else? Yes.
That gives you an indication about how much the data is different than the mean.
Okay. That is common with all the measures of dispersion. The things which you are saying is the general definition of measures of dispersion. A more specific definition for a standard deviation is it gives you the average difference between the data and the mean. Or the mean, yes, we are using the mean, yes. The average difference between the data and the mean. The data has 100 values. And mean is how many? 1 value. So if I take the difference from the mean, how many differences I will have? 100, right? Each value taking difference from the mean, you will have 100 differences, right? If you take the average of those differences, that will be somewhat close to standard deviation. Obviously, we don't calculate like this, but the idea behind standard deviation is to know the average difference between the mean and the rest of the data. Clear? Okay. Now, for standard deviation, we have two equations. Okay. Why? Because our data is different. Like we had for mean. You have a simple equation of mean, right? Summation upon number, right? But we didn't use it here. The example which we didn't use summation upon mean. We did summation of a product upon mean, right? Okay. People who have short-term memory loss. Okay. So we didn't do summation, direct summation of values. We do summation of some product, right, upon number of values. Why? Because our data is different. It is frequency data. We have groups and we have its frequency. Okay. So this equation which you see is when you are directly dealing with the values. No groups, no frequency. Okay. We will use it in some other cases. We'll use this in some other cases. But for frequency distribution data, we use this. This is the equation for standard deviation. When you have frequency distribution data, the data which we have. Now in our data, what was n? You're thinking everything down.
Number of vehicles.
Number of vehicles where? Observed in each group. Okay. N was number of vehicles observed in each group. What was S?
Speed.
Which is speed? Upper, lower, middle, final, mean. Middle of each group, right?
Yes.
Middle of each group. What was X bar? Mean. Okay. X bar is the mean. Okay. And this is the value from which we are taking the difference. Okay. and then capital N was total. Okay, capital N is the total number of values in your entire data set, summation of all the groups. Clear? Small n is for each group, capital N is for all the groups. Clear or not? Okay, so this is the basic equation, and this is the simplified or expanded version of the same equation. So this one and this one are same. They are not two equations. Okay, we have basically two equations. This one and this one. Okay, this one is used when? Huh? When you have no frequency, row values. Okay, and this one is with the frequencies. And this one can be transformed into this one as well. Okay. People who think this one is wrong, they can use this one, no problem. Okay, people.
This one is faster like that.
Huh? I told you, your calculator can process this data for you. You give the middle, you give the frequencies and the middle value, it can calculate this standard deviation as well. Okay, so faster, slower, doesn't matter. Clear? Clear? Okay. What happened to that chair?
Making noise maybe.
What happened to that chair? It was empty.
This one.
This one, what happened to this one? It's making noise, you made all the noise. Okay. Got it? Okay, now from here to here, what did we do? We had opened this bracket. Okay. So you have n multiplied by both of them, right? Okay. What is summation of n? Summation of n is capital N. Okay. Here when I multiply n with s, every group has a different n and every group has a different s. Okay. So here I cannot do anything. Okay. Keep it as it is. Here x bar is what? Constant or changing? Constant. Okay. So I can do simple summation of n, and that simple summation of n becomes capital N. Okay. And the x bar square stays as it is. Okay.
We should start with the square, then we apply n.
Mm-hmm.
We should start with the square. Open the bracket, then we apply it.
Yes. Okay. Clear? Okay. But the point is, the last two equations are same. They are for the same data set which we have. Okay. How do we calculate it? For that, we already developed this column, the last column. Okay. This is the thing which we need to calculate the standard deviation using the last equation. Okay. The expanded version. Okay. So the equation is this one. I'm talking about this equation. Okay. Okay, so what do I need? I need x bar, right? X bar was calculated in the last lecture, and it was how much? How much was x bar?
48.2.
Okay, tell me what is S? How much is S standard deviation? So this is this one, n, capital N, number of values, x bar, okay, and that's it. How much is it? Good. Everything good? Why are you laughing at you? Is he a friend? He doesn't wear the cap. Kick him out of the group. Make him your friend.
I got 60.
What? He's nobody's friend. Yes.
6.06.
6.06.
Check. Okay.
I don't check, I don't care.
No, the equation of
Sorry?
this equation.
Yeah. Okay. Any problem, any questions? Okay, now there's a check when you calculate standard deviation. Obviously, you have the mean already, right? Without that, you cannot calculate standard deviation. So you can perform the check that the standard deviation should be less than the mean. Okay, standard deviation should be less than the mean. If it is more than the mean, either you have a problem with your calculations, or either you have a problem with your data. Okay, you will be doing it for your data as well. Okay, so don't just accept any value, you have to check. Okay, why it should be less? Because mean is in the middle, right? Mean is in the middle, and if your standard deviation is more than the mean, that means what? You are going away from the mean by more than its own value. So you will go negative, right? This is the mean. Mean is what? 48. If I get a standard deviation 50, so 48 minus 50, 48 minus 50 is minus 2, right? This is the difference, right? I told you. The standard deviation is the difference from the mean. Okay. So if the difference is higher than the value itself, you are having a negative value, right? Can the speed be negative? Not in this universe, right? Right? Looking at this. Go see some Marvel movies. It's looking at me. Okay. Whatever. Speed can be anything. But here, not with us. Okay? Clear? Okay. So as a check, when you calculate the standard deviation, check it should be less than the mean. If it is more than the mean, check your calculation. If they are correct, then check your data. Okay? Other measure of dispersion is percentage of weakers within the pace range. Okay, this is where I have the pace. Okay, which graph? Tell me, which graph did I use to find out the pace? The upper one. Okay, and which range was I looking for? The range which has what? The highest number of drivers, right? This is what we defined as a center. The one which has more drivers in it. Okay, so we found that the pace is in this range. Okay, we said there are more drivers in this range, but how many? Okay, so the range itself tells you the center of the data is here, but how many are within this center? What percentage of drivers are within this center? Okay, this will become our measure of dispersion. Okay, so what we do? We come to the second graph now. So the pace from the first one, the range of drivers in the pace from the second one. Okay. Now I have what? Two values, right? So I will plot these two values here, 42.5 and 52.5, right? Somewhere here. Where is it? This one. Okay. 42.5 and 52.5. Okay. I have the two values. Okay. So I plot the values. I go to the curve and find out its percentage. Okay, so the percentage for 42.5 is 16%. 42.5 go up. Okay, where is it? Something happened. Sorry. Yeah, 42.5 go to the curve. The percentage is 16%. Now which percentage is it? This is cumulative. Okay, cumulative means it's not at 42.5. It is from 0 to 42.5, all of them, right? This is the meaning of cumulative. So, and we do the same thing with 52.5. So So I come here 52.5, I go to the graph and I find out the percentage. Okay, this percentage is how much? 77. Again, it is cumulative, meaning it is not at 52.5, it is from 0 to 52.5. Got it? So 0 to 42.5, 16. 0 to 52.5, 77. If I take the difference, I will get the percentage between them. Clear? Clear? Any questions? So this is the range I have for the drivers in the pace. Okay? So the center of the data lies between 42.5 and 52.5. And how many drivers are in this range? 61%. Okay? Clear or not? Okay. If I take some other data and I can find out the pace and I find out this percentage, here it is 61%. For that data, let's say it is 55%. What would you say about the variation in these two data sets? Which one has higher variation? Which one has lower?
The second one is higher.
The second one has higher variation because the center of the data is weak. Here the center is stronger, right? More values. If you reduce it, the center becomes weak. Center becomes weak means more variation. Clear or not? Clear? Okay. What about the standard deviation? Here standard deviation is 6. If it becomes 8, is the variation increasing or decreasing? This is very simple. Increasing, right? Because it's a difference from the mean. The difference is increasing, the data is okay. Varied. What? Clear or not? Any questions? Okay. The last measure of dispersion, again a range. Okay, it's a range. Even standard deviation is a sort of a range because this is the difference between the mean and the data. So you start from the mean and then you go up to standard deviation. So it's a range. Okay, so all measures of dispersion are ranges. Okay, this one is a range, pace is a range, and the standard deviation is also a range. Okay, we focus on this range on two percentiles, 15th percentile and 85th percentile. Okay, what is the meaning of a percentile? What is a percentile? Yeah? Location of the data, yes. You were saying something?
I said the percentage of the data that comes before.
Very good. Yeah, okay, you get the idea. Okay, so yes, it tells you the location in the data set, okay, or the percentage of data which comes before. Okay, so if I say 15% of the data, 15th percentile of the data is 40 miles per hour. That means 40% of the data comes comes before or till 40 miles per hour. Okay, so where the exact 40% of the where exactly the 15% of the data lies at 40 miles per hour or less. Okay, this is the meaning of the percentile. Clear? So when we say 15th percentile, that means 15% of the data lies at this value or before. Okay, and same thing with 85th percentile as well. If I say 85th percentile, 85% of the data lies at this value or before. Okay, when we say this value or before, which percentage we are talking about? Cumulative, right? The cumulative percentage. So all percentiles are taken from this graph. All percentiles are taken from this graph. Okay, if I take 50th percentile, 50, what do we call it? Median. Okay, 50th percentile is median. Mean can be more or less. Okay, because in mean you take the number as well, number of values. Okay, for median you are not looking at the value, you are just looking at the center. Okay, so 50th percentile, 50 is the median. Okay, So now I have two percentages, right? 15% and 85%. I need their values. Okay, where are the percentages? Y-axis. Where are the values? X-axis. So I start from Y-axis. This is my 15%. I come here to the graph, find out the value. Okay, for this data, the value is 42.4. Then I do the same thing for 85th percentile as well. 85%, go to the graph, find out the value. Okay, for this data, the value is 54.7. Okay, clear now? Okay, what percentage is within these values? Tell me. What percentage of drivers are within these two values? One is 15th percentile, the other one is 85th percentile. You already did the pace, right? So what percentage is within these values? 70%, right? 15% you left on this side, 15% you left on the other side. Okay, so between these values I have 70% of the drivers. Clear or not? Everybody, any questions? Any confusion? Okay. So 70% is a big part of the data, right? 70% is a very big part of that. So we are not leaving it to the values. For in the case of pace, you can get 60%, 70%, 80%, 50%. The percentage is not in my control, right? Here, whatever the range is between these two values, I always have 70% of the drivers. Right or wrong? Okay. So can you say that this is the most normal range of the data? Where you have 70% of the drivers, this is the most normal range of the data. Okay. Usually, statisticians say that if you are looking for outliers, values which are very high or very low, you should look at the extreme 15% of the data. The extreme 15% of the data usually have the outliers, meaning values which are very high or values which are very low. Okay, so this range tells you the normal of the data. Clear? Okay, and again everything goes back to which is chosen by the driver. This one is chosen by 70% of the drivers. This is why it is normal. Got it? Clear? Okay, so when you are dealing with design of signals, design of walkways, something, okay, then we deal with this range. We use this range in our design. Okay, if I'm looking for the highest value, I'll not design for the highest, absolute highest. I'll design for how much? 85%. Okay, there are drivers who are faster than that, right? So what do we do then? Do with them? Kill them, obviously.
They will kill themselves.
They will kill themselves. We never kill anybody, right? Still not. Okay. And if you have to design for the lowest value, if in some cases we use the lowest value of the speed, then you will not use the absolute minimum. You will use 15%. Okay? Clear? So, another thing which we can do with these two values is calculate an estimate of standard deviation as well. The equation which you see here, okay, it gives you an estimate of standard deviation. Okay, so if these values are this much, what is the standard deviation? Tell me.
6.15.
6.15. And what was the standard deviation earlier?
6.7.
So you can see the difference is very small, right? Okay. But you can get a difference. They will not be exactly same every time. Okay. And the amount of difference depends upon your values, your data. Okay. In some other cases, the difference could be more as well. Clear? Okay. You have this very simple small equation, and you have this very scary type of equation. Okay, Which one would be preferred? The scary one. Okay, that's why you are becoming engineers. You could have lived your life happily somewhere else, huh? But you had to come here. Okay, so this one, because this is more accurate. Okay, this is more accurate, more authentic. Okay, when you do more work, it becomes more authentic. I told you that last time, right? This is how you learn. So that is the actual equation for standard deviation. Okay, this one. The other one is just a makeshift arrangement. Okay, any questions? So we have covered two types of statistics from the speed data, central tendency and dispersion. Now we will do some more analysis using these statistics. Okay, so this is now the next stage. Okay, we are not always dealing with, okay, just give me the mean and standard deviation, I am done. No. Sometimes we need more from the data, but that will come from these statistics. Yes? Sorry? Till where?
Till we get.
Huh?
Till lecture 3.
Slide 20. Okay. The next thing is, if you remember when we plotted the speed data distribution, the frequency distribution, okay, we didn't join all the points. Okay, we made a curve and we called it what? Best fit curve. Okay, when we made the best fit curve, what was the aim? Why didn't I join all the points? It's easier. Why did I have to make a best fit curve?
No zigzag.
Huh?
No zigzag.
What's the problem with zigzag? It's good, right? You have fun doing zigzags. Hmm? So why statistics have a problem with zigzag? Huh? Trend of the data. Okay. So there may be some values if you start following them. I already told you about the outliers, right? So there are always some values which are out of the trend. Okay. So if you follow those values as well, you will lose the trend. Now you see the shape, right? You will lose this shape. Okay. So we will not see the general trend of the data. You want to see the general trend of the data. Okay. Not where all the values are going. Okay. I was interested in looking at the general trend of the data. General trend of the data follows this shape of the curve. Okay. And this shape has a specific name. It is called a bell-shaped curve. Okay. And now you know why it is called a bell-shaped curve, right? Okay. There are a couple of important points about this shape. First of all, if you take data about any real-time observation, if the data is about anything which is happening in real time, weather, rain, student grades, and what else? Traffic speeds, traffic flow. Okay, you take any other example. Okay, from environment, from structures. If the data is coming in real time and you have enough values, okay, then the statisticians say that it should follow this shape. This is the most natural shape for a real-time data set if you have enough values. Okay, obviously you cannot make any sort of shape if you have 3-4 values, right? You will not get a curve. So you must have enough values. This shape is called bell-shaped curve. It is naturally suitable for real-time data, and there are two important properties of this shape. First of all, how many peaks you see here in the shape? One peak. Okay. There's only one peak and then goes down. On both sides of the peak, it goes down. Where is the peak? In the middle. Almost. Almost. Obviously, real-time data. It will not be exactly in the middle always. Then, obviously, if it is exactly in the middle always, then you know the value beforehand. It's not possible. Okay, I know I start from 30 and I go to 60, so if it is always in the middle, it is always 45. Okay, so it's not always in the middle, but it is very close to the middle. Okay, so these are two things about the bell-shaped curve which we say that it should be following the real data should be following that. Okay, any data which follows this shape, okay, is called to be following normal distribution. Okay, so if you have frequency data, you plot frequency curve and you get this shape, we will say data follows normal distribution. Okay, clear? Now if the data follows normal distribution, then there are two important items of the data. We already calculated them. One is mean, the other one is standard deviation. Okay, or the variance. Now who will tell me what is the difference between standard deviation and variance? What is the difference between standard deviation and variance? Square, right? The square root goes off for variance. Okay, so if you have a standard deviation, you have variance. If you have a standard deviation, you have variance. Okay, so this is how we represent the data which follows normal distribution with its mean and variance. With its mean and variance. Okay, x follows normal distribution, mean of 40, variance of 25. Okay, now if I write the same expression for my data, the speed data, do we have the mean? We have the mean, right? And we have the variance, we have the standard deviation, which was 6.06. Okay, so what will be the variance? Tell me. For my data, variance is how much? For 6.16 square, right? It's not 36 point something. It was 06, sorry, 06. 06, okay. So, how much? 36 point? 36 point. Clear? This is the variance. Okay?
76 hates the rounding up and rounding down.
Yes.
Why you rounding?
Because I hate statistics.
You hate me?
Yes. Okay. So if I want to write a speed data follows normal distribution, I will write it like this. Speed represented with S, N for normal distribution. I have to write the mean. My mean was 48.1 and the variance is 36.8. Clear? It's just an expression. It's just an expression. Okay? So whenever you are telling about distribution of any data, you need to give the other person some key statistics of the data. For normal distribution, the key statistics are mean and variance. Okay? There are other distributions as well. The data always does not follow normal distribution. Like the accident data does not follow normal distribution. Although it's natural, still does not follow normal distribution. Okay? So it will follow some other distribution and it will need some other statistics to represent. Okay? So we are not always dealing with normal and we are not always dealing with mean and variance. Clear? Clear? Okay. So that's why you cannot just assume every time. Just, okay, normal. Whatever I get is normal. Okay? You have to see. We have another variation of normal distribution. There's a variation of normal distribution, which is a standard normal distribution. Okay? And this is how I represent a standard normal distribution. Now who can read this? What does it say? What does this say? Huh? For Z distribution, what does this say?
Mean zero variance.
Same. Okay. Yes. So it's a normal distribution which has mean of 0 and variance of 1. Okay. Anything which can be represented with this is not any normal distribution, it is standard normal distribution. Got it? So this one is normal distribution. This one is normal distribution. This one is standard normal. Okay? Clear? Okay. Now, what did we do with standard normal? all normal distribution have this shape, right? Okay, and now I did what? I said standard normal has fixed values as well. Standard normal has not only the shape fixed, but the values are also fixed. Okay, so if I have a standard normal distribution, because the values are fixed, I want any percentage of data, I have tables available from which I can get the percentage. Yes. Okay, like in the previous case, in the example we were finding out 85th percentile and 15th percentile, so you have to plot the data, right? You have to plot the data and find out these things. For a standard normal, you don't need to do that. Okay, the graph is already plotted, values are already found, and they are stored somewhere. Okay, so you just go there and look for the value. Clear? Okay, so having a standard normal will make my life easier. Having a standard normal distribution will make my life easier. Okay, but the problem is, can I have a speed data which has standard normal? Can a speed data have a standard normal distribution? Normal it can have, it should have. But can it be standard normal? Why not?
The mean is 0.
The mean is 0. Cannot have a speed mean 0. Right?
Should.
Yeah, I'm agreeing with you for the first time. Okay, so the standard normal is not something which you can have naturally, okay, because of the mean and the values. So what do? I still want to use the table, the values which are given for a standard norm. Okay, so what do? We do the conversion. Okay, it's like the equations which we are using, or the equations which you have used in other courses. So the equation is in meters, but somebody gives the data in feet. So I cannot use the equation, but I have this equation. So what do? I convert the data, right? Same thing here. Okay, so we take our data, we convert it using this equation. Then it becomes standard normal. Okay, from normal it becomes standard normal. Okay, how do we convert it? Take any value from the data. X is any value in the data, any speed value. We are doing a speed, right? X is any speed value minus the mean upon standard deviation. This is the standard equation. Okay, like this is the equation which you will see in most of the books. Okay, so it does not use X bar and S. Okay, it uses the typical statistical terms, which is mu and sigma. Mu means mean, sigma means standard deviation. Okay, so you can take your speed data, this table, convert the values from that equation, that formula. Okay, you find out the mean, standard deviation, convert all the values. Then you don't need to worry about the percentiles and medians and these things. Okay, you have them available with you. Okay, now this is very important for your term projects. Okay, this will be the first step before you go on and collect the data, which is to find out the sample size. Okay, which is to find out the sample size. How many samples you need to collect. For the first iteration, for the first submission, I told you at least collect 10. Okay, some of you collected more, some of you collected not less, but some of you collected exactly 10. Okay, but now for the second submission, you need to find out how many values actually you need. Okay, so for that we need to calculate the sample size. For any data set, when you go on and collect the readings, collect the observations, you need to set for yourself error value, an acceptable error value. This is acceptable error. You can bear me up to 40 minutes. Okay. So what is the acceptable error of the value? We get it from here. Okay. Small capital E is the acceptable error which you can expect in your data. Expected error, acceptable error, whatever. So standard deviation upon number of root of number of values. Clear? Okay. So this will give you how many values you can expect. Then I need to set for myself a confidence level for my data. Okay. For example, when you somebody asks you that, let us meet at this place, and you are coming out of your house, so you have an idea about your time, right? Okay, that I will reach this place in these many minutes. Okay? Is it exactly the same every time? No, there is a variation, right? So what is the percentage of times you can be wrong? About the estimate you are giving me, what is the percentage of times, or let me rephrase it, what is the percentage of times you can be right? The value which you are giving me, what is the percentage you are confident about this value? What is the chance that you will be in this value? That is called as confidence interval or confidence level. This percentage is called as confidence interval or confidence level. Okay. From where do I get this confidence level or confidence interval? We said my data follows which distribution? Normal distribution. Normal, right? Standard normal we will make it, but it is normal. Okay. One more thing, you can convert normal to standard normal. You cannot convert something which is not normal to standard normal, because you are then changing the entire data set. When you convert normal to standard normal, I'm just changing the values, right? Converting the units, converting the values. Okay. Something which does not have this shape, it is having zigzag up and down, or it is having two peaks, or the peak is on one side or the other side, it's not normal. Okay. So you cannot just put it in this equation and say now it will become normal. No, it does not work like this. Clear? Okay. It's like if I give you the length in meters, you can convert it to millimeters, right? You can do this much. And you cannot convert the length into volume. You cannot say, okay, this is meters, I will make it in meter cube. No, it will not remain length. Same thing here. Got it? Okay. Going back to the point, we have the data which follows normal distribution, standard normal or any normal. Okay, it doesn't matter right now. You can, on normal distribution, we can apply a theorem which is called as central limit theorem. Okay, central limit theorem tells you if you select a percentage of confidence for your data, okay, then how you can get the range of that percentage. Central limit theorem deals with giving you a range for a percentage of the data. For example, it says that if you set your percentage as 95%, I want to be confident about my data 95%. In other words, I want to be right about my data 95% of the times. Okay, so what range will make me accurate up to 95%? This range will come from central limit theorem. Okay, and the central limit theorem is very easy. It says that if you want a range, take the mean value plus minus something into E, where E is what? L. Got it? Okay, and this something depends upon your confidence level, the percentage. Okay, this value which you see, 1.96, if you want the percentage of the times you are correct to be 95%, then this is your range. Okay, if you calculate this range for any data set, then 95% of the times your data will be in this range. Got it? Clear? So for example, you took a sample. Okay. Now somebody says that this is sample on 1 day, 1 hour sample. Okay, I cannot trust that it will always be like this. The values will always be in this range. Okay, give me something more. Now, can you keep on collecting the samples? No. I can use central limit theorem assuming that my data follows normal distribution. I can use central limit theorem. I will calculate the mean and the error of the data, and I will calculate this range. Now I can tell my client that my data is in this range 95% of the times. Whether you collect it now or tomorrow, after 1 hour, after 3 hours, doesn't matter. What?
96.
Is a constant which is for 95% range. Okay. If you change the range to 99.7%, this number will also change. it will become 3. Clear? Central limit theorem, the idea of central limit theorem is any confidence interval in the data can be represented with a range of x bar plus minus a into e, where a depends upon your percentage of confidence. Okay, for 95% a is 1.96. For 99.7% the percentage is the a is 3. Got it? From these values, 95% is the most common value. 95% is the most common value. Okay, so most of the times we use a as 1.96. Clear? Any questions? Okay, now if for my data, the data which has a mean of 48.1 and the standard deviation of 6.06, what is my E? How much is my E? So standard deviation is 6.06 divided by the square root of the number of values. Okay, so my number of values are 368. 0.31. Okay, so this is my acceptable or expected error. Okay, then how much is this range for my data? The 95% range of my data, the 95% confidence interval of my data. How much is this? You see the mean, you have the E, and you will use 1.96 because we are talking about 95%. How much? Huh? Yeah, plus minus me. The range. You will give me the range, right? You give me this.
Yes.
Yeah, the range. We call it confidence interval. The range is called confidence interval. The percentage is called confidence level. Okay? Clear?
$47.5.
47.5 and 48. Okay, so if somebody keeps on collecting samples after samples at the same location with the same drivers, 95% of the times his values will fall within this range. Clear or not? Anybody has any question? Clear? Okay. So you have a sample, but you want to give an idea about the entire population of drivers. How will they behave? This is one way of doing it. Okay. Now, how is it connected with the number of samples? Now, you see in this equation we are using what? We are using this E, right? Okay. And this is what? Number of samples. This is what you want to calculate, right? This is what we want to calculate. So this whole thing equals to E. And E was what? Error. Okay. So if I can fix the error, if I can fix E, I can get what? Number of values, right? If I can fix E, this is my equation, right? Okay. So I have standard deviation and I have N. And I'm calculating E. If I fix E, I can reverse it, right? I can calculate N. Okay, so this is the idea we are using, but we are not interested in calculating E. We are interested in calculating this whole thing. Okay, because in the end, you are looking for a range, right? Okay, and your range depends upon E and this value, both. Right or wrong? Your range depends upon E and this constant, both, right? Okay, so we will not fix E, we will fix this entire thing. Okay, we will fix this entire thing, which is the variation which I am going forward and backward from the mean. This is the mean, right? Okay, so I'm not only fixing E, I'm fixing the entire range which I am going forward and backward. Clear? Okay. But what's the difference? This is a constant, right? So still I am fixing. The only thing which I can fix is what? E. I cannot fix this. This is 1.96. It's from the theorem, right? Okay. So if you want to calculate the, this is what we have done. Okay. So if you look here, if you go with 95% confidence level, central limit theorem says from the mean you can go 1.96 E plus or minus. This is what we just did. Okay. So this whole thing, this is capital E, and this whole thing is represented with small e. Okay. So I have this equation. Small e equals to 1.96 capital E, where capital E is what? S upon root of n. Okay. So if I want to calculate n, I'll fix E and take n on one side, E on the other side, right? Okay. So what will I get? I should get this one. It was E 1.96 S upon root of n. Right? Clear? To remove the root, I have to do the square, right? This will become E square. This will be 1.96 square. This will be S square. This will be n, right? Okay. So n will go here. 1.96 square is 3.84. Square, S square, and under E square. Clear? Any questions? Okay. This is for how much confidence level? 95%. Okay. If I change the confidence level, then this number will change. E will remain. This number will change. Okay. So again, this whole thing will become small e. Okay, and we'll do the same thing here. Instead of 1.96 square, it will be a square of 3. So instead of 3.84, you see 9. The rest of the equation is same. Clear or not? Any questions? Okay. So these are the equations which you can use for finding out number of samples. Okay. Now what do you need in these equations? You need, if I want to calculate number of samples, I need 3 things. What? Error, small e, right? It's given in your term project guidelines. The value of a small e, not capital E. Small e is given in your term project guidelines. What else do you need? A standard deviation. From where will I get the standard deviation? I need some values, right? I need some values. Those values you have collected in the first submission. So you will use those values to find out your standard deviation. Okay, and yeah, the constant. Should I use 3.84 or should I use 9? Okay, that depends upon my confidence level. Okay, so this is the one which you are using. You will use the first equation. Okay. Clear? E is given, confidence level given, S from the first submission. Got it? Clear? Any questions? Okay. So for example, if you have this problem, we have to find out how many speeds must be collected to find out the distribution of the, as I mentioned earlier, if you want to find out the distribution of the data, you must have enough values. Okay, this is why we need number of samples. If we just collect 10 samples and 15 samples, we are not sure whether we are getting the distribution or not. This is the whole idea behind the number of samples. Okay, even 5 samples are values, 10 samples are values, 100 are also values. Values from the same place, right? Okay, but why will we go for calculating number of samples? So that when we get this much number, I know I am getting the whole distribution. Okay, this is why we need to calculate the number of samples, so that in the end I get the whole distribution. Clear? Okay, so if you want to be accurate within plus minus 1 and confident up to 95%, what are the number of samples? And if you want to change the error level to plus minus 0.5 and confident up to 99.7%, then what will be your what are the number of samples you need? Okay, so I will make a table here. Because I have two values of error and two values of confidence interval. Okay, so I will calculate number of samples, confidence interval, and the error will go here. Error is once it is plus minus 1, for other time it is plus minus . Okay, the confidence level 95% or 99.7%. Okay, these are the equations I've been using. Okay, tell me value for each case. Did you guys give me the phone? Have you seen my phone?
This is your phone?
This is my phone.
Yes.
Why is it charging?
You don't want? Okay. Frozen for this.
Yes, how much?
So we don't know the standard deviation.
We don't know the standard deviation. Yes, good question. Okay. Now I told you how you will calculate standard deviation for your project, right? Because you have values. Okay. So the normal procedure is you take an old data set like you will do for your project, and you will make the calculation using the old data set, because new data set will still be collected. So you don't know the standard deviation of the new data set. You only have an old one. Okay. So once you the other method is I don't have any new data set, I don't have any old data set. Okay. So I will assume a reasonable value of a standard deviation. I'll assume a reasonable value of standard deviation. Okay. In this case, they are assuming standard deviation to be 5. But this is only to be done when you don't have a data set.
No, we will use 6 or 5.
5. Clear? Yes, tell me. Yes. How much? Huh? Here E is 1, here it will be 0.5.
So for 95 confidence level and 1 error,
Hmm.
96.
96.
For 0.5, no, so then it's 184.
Same confidence, right? Same confidence. 384. This one? Huh? 225 and 900. Okay, you can see some patterns here. Again, just as a check for your calculations. You need less error, you need to be more accurate, right? You need to be more accurate, you need more samples. Okay, same thing with the confidence level. Same thing with the confidence level. You need to be more confident, meaning you need to be more accurate, right? So again, you will need more samples. The same thing you see here. Okay. Now here the values, I don't know if you already rounded up or rounded down, but the values are given as complete values. But from the equation, you may get a value 5 point something. Okay. Let's say if it is 5.9. I cannot collect 5.9 samples, right? I'll collect how many? 6. And if it is 5.1, then still 6. Still 6. Okay. You cannot round down in this case, because your value is associated with an error. If you decrease the value, the error will increase. This is what we said, right? When you decrease the error, values increase. So vice versa. If you round down, your error will increase. Now we made an assumption here, right? For calculating these values, we made an assumption. What was the assumption? Standard deviation. Okay. And in some other cases, like I said, you may be taking it from an old data set, which could be for some other place as well. I'm talking about that case, okay, not your case. Your case is you are on the same highway and the data is very recently collected, so you don't need to perform this check. But if you made an assumption just out of your mind, or if you took a data which is no longer valid in this case, it was taken many years ago, it was taken from some other highway, okay. After you make the assumption, after you calculate the number of samples, okay, so somebody says that I'll pick this value. This is very reasonable, low value, and it is enough. The error is enough, the confidence level is enough. Okay, so I'll go and collect 96 values now. They go and collect 96 values. They will calculate the mean and standard deviation of those 96 values. Now they have the actual standard deviation now, right? This is the actual one, not the assumed one. Okay. They will come back to this equation, put the actual standard deviation, and check how many samples are they getting with the actual value now. Okay. If those samples are less than 96 with the actual value, if the number of samples you get is less than what you already have, good or bad? Good. Okay. You already have more than required, and vice versa. Okay. If you required more, you have less, you go and collect the difference, obviously. Okay. So the actual comes out to be 100 now. So you need 4 more. Okay. Got it? Clear? Any questions? Okay. Another thing which we do is when we have done, I mentioned this type of study as a follow-up study in the previous lecture. Like the slides before that, it was mentioned as a follow-up study, okay, or an observation study, means the same thing. In a follow-up study or before and after study, you are looking at the effect of a change on the road. What is the effect? I made a change on the road. What is the effect of that change? Clear? This is what we call as before and after study, follow-up study, observation study. Okay, all these means the same thing, that there is a change on the road and what is the effect of the change. Clear? Now, in this case, you need 2 samples first of all. You need a sample before the change, you need a sample after the change. That's why we call it before and after. For both samples, you will calculate mean and standard deviation. So you have how many means? 2. And you have how many standard deviations? 2. Okay, and you have 2 number of samples as well, right? One for before, one for after. Maybe you collected 50 values before, now you are collecting 60 values. It can happen. You can collect unequal samples. You can collect unequal samples. Okay? Equal is better, but unequal will still work. So how do we see the effect of the change? We see it, and I will show you with the example why do we need to do the test. But we do a test basically. We do a test which is called as the Z test or T test. Means the same thing. Z test or T test, depending upon how many values you have. If you have a small number of values, we call it T test. If you have enough values, we call it Z test. Okay? But the procedure is same. The equations are same. I will replace z with t here if the number of values are very small. Okay, but procedure is same. Standard deviation before, standard deviation after. Number of values before, number of values after. Okay, this will give you sy. Using sy, you will go to the z value, mean before, mean after. And what is sy? Comes from here. Okay, in the end you have what? A z value. Okay, now I represented z, I represented something with z. What was that? A standard normal distribution. Okay, and what did I tell you about standard normal distribution? That it has what? Mean 0 and 1 variance or standard deviation, which makes what? Then I can have, if no, not the conversion. If the mean and variance is fixed, then that means what?
I have also known that.
The values are fixed. Okay, so they are the z table. Okay, which I can use now. So once you calculate the z value, okay, I can go to the z table now. This is the z table. Okay, have you seen it before? Where? Statistics. So you know how to read it, right?
So we took the new cost to 7.6.
Still saw the z table. Okay. Okay. Those who did, okay, pay attention now. Okay. If I want to check a value 1.95, how do I check it? If my z value is 1.95, how do I read the table? Tell me. 1.95. My z value is 1.95. Yes. 1.9 from here and 0.05 from the top. Okay, and these are the percentages. The values in the table are the percentages. Okay, the cumulative percentages. The cumulative percentages. Clear? Clear? We have now. Pay attention. The proposition is we have a z value. I come to the table and find out a percentage. Now I need a rule. Now I need a rule. Okay, which percentage will I accept and which one will I reject? Okay, the rule says you will accept this one and reject this one. If the percentage you get from the table is 0.95 or more, accept. Less than 0.95, don't accept. Got it? Clear? Because as I said, we work on 95% confidence interval. That's coming from there. So what does it mean? Accept means what? We are doing before and after, right? Accept means change is there. Reject means no change. Clear? Clear? Any questions? Huh? You have two data sets. You can calculate z value. Clear till now?
Yes.
You take this z value to the table. Okay. From the z value, you will get the percentage. Then you apply the rule to the percentage. So if your z value was 1.95, 1.9 and 5. Okay, I get 0.97, which means 97%, right? I apply the rule. Where am I? Up. This one says accept. So that means accept meaning there is a change because of there is a change in speed. Before and after there is a change in speed. Okay. If I go in this region, this means before and after no change in speed. Clear? Okay. I'll just show you the example. You can do it yourself. Okay. You have two data sets. You have the mean. You have the standard deviation. You have the number of samples. Before, after. You can calculate z value and look at the percentage. Okay. And you can decide whether it is accepted or rejected. Okay. And you come back with it after the exam. You have the exam next month, right? You come back with it after the exam. Just one, give me 1 second. Now here, just I want to show why do I need to perform the Z test. What did you break? You throw something. I thought we have a competition. Okay, now pay attention. Look at the question. They want to reduce, whatever they did. Before sample speed, how much? 65. After sample speed, 63. Is there a change or not? There is, right? So why I'm making you calculate the Z value? You can see and tell me there's a change, doctor.
You want to know if that change is random or because of...
Yes. Okay. This is a sample of 50. This is a sample of 60. Okay. Maybe this 50 is only in this. This mean is only in these 50 values. If I got some other 100 values, the mean will change, right? And same thing will happen here. So the Z value will ensure that the difference is not random. Very good word. The difference is not random. Okay, the difference is solid, is significant, and it will always, it has a very high chance that it is the real difference. Clear? Okay. So when you come after the exam, the question is not finished. Just bring the Z value and the probability, and we will do the next step after that. Okay, but focus on the exam. Okay, thank you. Bye bye. Yes. Yeah, it's fine.